When we add and subtract radical expressions, the requirements are actually a bit stricter than multiplying or dividing. Not only do we have to have the same index like we do for multiplying and dividing, but we also have to have the same radicand. Once we do, we can simplify those individual radicals as far as possible and then add or subtract the coefficients. Let's see what we mean by looking at question 7. We're asked, what is the simplified form of each of these two expressions? Well, notice in the first one, our variables are a times the square root of 7bc. And in the second part of the expression, we also have a times the square root of 7bc. So we have the same index, the square root, and the same radicand, 7bc. Additionally, we have the same variable coefficient. So this is like saying, if I used a u substitution of a times the square root of 7bc, this problem is just 14u plus 5u, which you know is 19u. We can go back and put in the actual original expression and say, okay, that means our answer is 14 times a times the square root of 7bc. That's our final answer. You don't necessarily need to do that u substitution if you can just see that you're adding 14 of these plus 5 more of them, which gives you a total of, 19 of them. But if the u substitution is helpful, then feel free to use it. Finally, in part B, we look to see, do we have the same type of situation? Well, this radical is the fifth root of x. This is also a fifth root, but notice the radicand is different. If the radicand is different, we would look to see, well, maybe I can simplify it and the radicands could become the same. But 3 is a prime number. I can't simplify the fifth root of 3. These are not compatible. So we would say that this is already simplified. I'm not going to say that there's no solution because I wasn't asked to solve anything. I'm simply going to say, I can't simplify this. This is the simplified answer. Moving on to question 8. We're asked to model something using radicals and to then see if we can simplify the expression. It says this tile design is made of congruent right triangles, each with a base of 1 foot and a height of 2 feet. I've always found this diagram a little bit awkward, so I like to just take one of the triangles and draw them separately. We're being told these are all right triangles, and the base of each right triangle is 1 foot wide, while the height is 2 feet tall. So each of these different triangles is really a congruent triangle. So you've got 4 triangles. We're asked to find the perimeter of the tile. Well, notice the perimeter of the tile is made up of each hypotenuse. So there are 4 hypotenuses. So we've got the perimeter is 4h. And that means we need to use our geometry to find a way to describe h. Well, we all know the Pythagorean theorem. So that's one option. But you might notice that if this is the short leg, actually, let's pause. The short leg, we could have a hypotenuse that was twice as long and a long leg of the short leg root 3. So this actually isn't a 30, 60, 90 triangle, which is where I was thinking we could go with the problem. We are going to have to do it using the Pythagorean theorem. So let's look at this. We have 1 squared plus 2 squared equals h squared. Well, 1 squared is just 1 and 2 squared is 4. So this is 5 equals h squared, and h equals the square root of 5. We don't need a plus or minus here because we're talking about the length of a side, which will clearly not be a negative number. So the perimeter is 4 times root 5. Now, we were able to calculate that perimeter using a simple formula because it was a square and all 4 sides were the same. Alternatively, if we didn't realize that we could just multiply the length of one side by 4, we could have said the perimeter is root 5 plus root 5 plus root 5 plus root 5. We could have done it out. in which case we would have said, well, I have 4 root 5s, which would give me the same answer. So we can think about it either as a multiplication problem or as a sum. Looking at question 9, we see a problem that at first glance makes us think, oh, I can't do that. They're all square roots, they have the same index, but the radicands are all different, so they're not compatible. But when we're asked to find the simplest form of an expression, we want to be careful about making an assumption too soon. Perhaps we can simplify each of these individual radicals and maybe they will become compatible. So let's look at the square root of 28. Well, the square root of 28 is the square root of 4 times the square root of 7, or 2 root 7. When we look at the square root of 175, well, that's the square root of 25 times the square root of 7, or 5 root 7. This is looking promising because both of those radical expressions includes a root 7. So we look at the square root of 63. Well, that's divisible by 9. In fact, 9 times 7. So this is 3 root 7. And all of a sudden we see we would have spoken too soon if we said that this problem couldn't be simplified. So let's rewrite it as 2 root 7 minus 5 root 7 plus 3 root 7. So if I have 2 root 7s and you take 5 away, now I have negative 3 root 7. But if you then give me 3 root 7, I now have none. So this expression simplifies to 0. Let's take a look at number 10. In question 10, we're asked to multiply 2 expressions together that each contain radicals. So we basically treat these like binomials, and we've done problems like this when we studied imaginary numbers back in our quadratics unit. So first we would distribute 1 through the second expression, and we would get 4 minus 3 root 7. But then we're going to distribute 2 root 7 times the second expression. So 2 times 4 is 8, and root 7 didn't have anything to multiply. In the next expression, 2 times negative 3 is negative 6, and root 7 times root 7 is a 7. So really this last term is negative 42. Now we look to see if we can combine our like terms. Well, 4 minus 42 is negative 38, and negative 3 root 7 plus 8 root 7 is a positive 5 root 7. That's as much as we can simplify. The negative 38 and the 5 root 7 are not like terms because one of them has a radical and the other does not. Let's do the second part, 10b, the same way. First, we'll distribute the 5. So we have 25 minus 15 root 2. Then we'll distribute the 3 root 2. 3 times 5 is 15 because they're on the outside, and the root 2 doesn't have anything to multiply. Then 3 root 2 times negative 3 root 2. Well, the positive 3 and the negative 3 multiply to make a negative 9. And root 2 times root 2 is 2. So this last term is negative 18. Combining our like terms, we have 25 minus 18 is 7. And notice negative 15 root 2 and positive 15 root 2 are opposites. So we're left with just 7. This whole expression simplifies just down to that. The last problem we're asked to do here, we've also done something comparable to this back in our quadratics unit when we worked with complex numbers. So we have 11 divided by 6 plus root 3. Remember, I can't multiply by just the root 3 because that'll simply move the root 3 over onto the 6. I can't multiply by 6 plus root 3 because we'll just end up with a different term in the middle that includes a root 3. So instead, we multiply by the conjugate. The conjugate changes only the middle sign. So it's different than an opposite. We're going to multiply by 6 minus root 3. Well, 11 times 6 is 66, And 11 times negative root 3 is negative 11 root 3. In the denominator, it's like those two binomials, but you might recognize this as being a difference of squares, much like this last problem we looked at in 10b was a difference of squares. If you look at that product, it's the same two terms, but one time they're adding and another time they're subtracting. So we know the middle two terms will cancel out. That means that 6 times 6 is 36. We would then get a negative 6 root 3 and a positive 6 root 3, which would cancel each other out. Positive root 3 times negative root 3 is minus 3. So we now need to simplify the denominator. So our numerator is currently unchanged, but our denominator is 33. Now when we look at this, we should realize that 66, 11, and 3 are all divisible by 3. So we need to reduce this fraction. When we do, our final answer will be each of those terms divided by 3. So we have 20. I take that back. They're not all divisible by 3. They're all divisible by 11. I was thinking about where we were going instead of where we came from. So backing up, they're all divisible by 11. 66 divided by 11 is going to be 6. 11 divided by 11 is 1, so we just have minus root 3. And then 33 divided by 11 is 3. And that's the simplified form of the original problem.